And indeed, as you were saying, this is going to be a description of what we're doing under this name of Analysis Grand Challenge. And to get us started here, I'm going to have a few slides just to set a bit the scene, and then we're going to jump into a notebook and going to go through that and see things actually happening in practice. So a few things I need to explain at the beginning here. There's two words here, IRIS-HEP and Analysis Grand Challenge. So what IRIS-HEP is, it's a US software institute for research and innovation in software and high energy physics. So this is paid by the NSF. And what we're doing as part of this institute is we're doing research towards the high luminosity LHC. Why are we doing this? Because we're going to be taking a lot more data at the high luminosity LHC in the future. And the data processing methods that we're using for physics analysis don't scale so well if we don't get substantially more resources allocated in the future, which we don't expect. So we need to improve our methods so that we can still do all the interesting physics that we plan to do when we have much more data in the future. So that is what this IRIS-HEP Institute is doing, and there's different areas that tackle different aspects of that. Now, since there's a lot of different pieces that come together when you want to do a physics analysis, you not only need software to do that analysis, you also need resources on which you can run this analysis. And in fact, IRIS-HEP is working on quite a few of these different aspects in its attempt to provide sustainable analysis pipelines. One thing that we need then is when we have all of these different efforts to bring them all together. And this is what we're doing under this name of Analysis Grand Challenge. So it starts out as an integration exercise really for IRIS-HEP, where we take all the pieces we're working on and we're putting them together, we're putting them to the test, where we have a physics analysis that is realistic in scope and scale. And we test everything that's being developed, all the things available in the ecosystem, can we put them together and do they satisfy the requirements that we have? So it starts out as that. It starts out as an integration exercise that's bringing together all the different pieces here. Where we can deploy the software we're developing on analysis facilities, and we can demonstrate, yes, we can do physics analysis with that kind of setup in an efficient way. But then it goes beyond just this integration exercise, as I'm going to try and highlight in a second here. Now, I've said the word analysis a few times, so let me clarify a bit what exactly we mean by that, because depending on your background, you might understand different things under this word. So in view of the high luminosity LHC analysis here in the context of what you do as a physicist doing a physics analysis starts at some point from a common set of data samples that are going to be centrally produced and available to you. And then starting from that, all the subsequent steps that you need to do in order to go from that data to the results that you can publish in your paper is what we understand under this term analysis here in this context. So you're going to have to extract all the relevant data from these files that are going to be provided centrally. You're going to have various types of objects in there that you might need to calibrate or recalibrate, and you might need to evaluate different calibrations for the purpose of evaluating systematic variations that you need to consider. Then you probably aren't interested in all the events that are going to be available, so you're going to have to filter out those that you care about. And you also might want to calculate different types of observables that you're then using in your analysis to increase your efficiency. You may want to build histograms. If you want to do a binned analysis, you don't have to. But here in this case, we're going to be looking at the case where we do have histograms and do a binned analysis. And then from those, you want to build a statistical model that you can then use to perform inference and get the results that you ultimately can publish. In order to do so, you're also going to have to visualize all of these pieces to convince yourself that what you're doing is indeed the right thing that you intend to do. So there's various visualizations along the way that are crucial to be able to look at so that you can develop your analysis and that you can disseminate the results. And then you don't just want to do this once. During optimization of this analysis, you're going to do this many times to various extents in order to optimize your analysis. And then ultimately also you want to preserve your analysis so that it can still be reproduced, that you can rerun parts of it, that you can use it, for example, with a different type of signal in the future. Again, rerun a piece of it and get a new result out of that without having to put lots of additional efforts into it. So that is another aspect here of what we're looking into. Now, what is the task that we're trying to tackle under this name of Analysis Grand Challenge? This is what I'm describing here briefly. So it's about something that is quite common at the LHC, namely top quark pairs that are being produced, and we're doing something that is fairly simple in that context. We're from a high level point of view, then once you go into the physics details, it gets complicated, but we're measuring the cross-section of top quark pair production in a specific final state. That includes a few pieces that we're going to be looking at in a second in the notebook, where we're constructing a top. You can see a plot as a spoiler for the notebook on the right here. And it's a fairly simple setup, but it's one that is quite flexible and can easily be extended to capture various other types of use cases that you might have in practice at the LHC. And one thing that we're focusing on specifically here in this setup compared to other types of example analyses is that we want to demonstrate also the handling of systematic uncertainties, as those are something that people in practice need to deal with, and that can be a complicated thing to handle. So we want to focus on getting a nice workflow that handles those well. We are using open data from the CMS experiment, and it's important to us that we do so because by us using open data, it means that you can actually run this analysis with us. You can go on and use the notebooks that we're providing here and do your own analysis with that. All of that data is publicly accessible and available to everyone. And in total for this year, we have about 4 terabytes of N tuples available. We're not processing all of them today. I have to tell you, unfortunately, Binder isn't going to give us that much compute for every single participant, but you are processing a piece of that data set if you're running along on Binder. And I want to stress that the setup that we have here is not meant to discover any types of new physics or make a really detailed physics measurement. What we're looking at here is demonstrating a workflow and demonstrating functionality, but all the physics details are not going to be correct because we're focusing on that functionality. And if you really want to extract physics from that, you're going to have to work more on implementing all of the systematic variations, for example, in the correct way physics-wise, but that is not the focus of what we're doing here. So this demonstration is about functionality. What I have on this slide here in this figure on the bottom right are the points that analyzers typically suffer from when they do a physics analysis. And the number 1 point here is the handling of systematic uncertainties. We'll see in a second how we do that in our kind of setup. But because those points here are those that analyzers name when you ask them, okay, what is difficult to do? Because of that, we're focusing also on a setup where we do hit and touch on all of those points so that we can test, okay, how is the workflow in our kind of setup and how painful are these different points so that we can evaluate then also what can we improve so that the user experience in the future is going to be better. There's going to be a lot of different libraries, services used in our demonstration. You can find some logos here. We'll see more in the notebook in a second. Those are also all links. If you want to look at any of the libraries here in particular, just click on there and you will be brought to more information. So this is just to say we're really trying to bring together a vast offering that's available here in this ecosystem in order to do a physics analysis with all the pieces required. Now, today, you're going to be able to run on Binder, but in practice, if you're trying to process large-scale physics data sets, that's not going to be sufficient, and you're going to have dedicated resources available to you. And one thing that we're also investigating and developing in the context of IRIS-HEP is this prototype analysis facility under the name coffea. I'm going to be running the demonstration from there today myself. It's going to be the exact same notebook that you're also using. But this is something that we're developing and using to test how we can perform physics analysis that we then can also scale to additional resources so that given that we have these resources available on these dedicated facilities, we can actually perform analysis efficiently and in a sufficiently fast way for fast turnaround time so that people can quickly get to their physics results that they care about. So lastly, here on this slide, next steps and plans for the future. This project is ongoing, and there's various directions in which we want to expand. So the analysis that I'm going to present, we would like to expand in a few ways, most notably adding a machine learning component. We have different implementations of the analysis task available. You will find them also linked in the notebook, and we're curious to compare them in order to see how the usability and the performance of the various different approaches looks like. Next, we're moving on to benchmarking to study at scale how the performance is. And in the longer term, what we also have as a stretch goal is related to what Nathan was just showing in the earlier session. We would like this pipeline or part of the pipeline at least to become differentiable, so you can automatically optimize your physics analysis as well. If you would like to stay in touch, please join us on this mailing list down here where you can sign up. And I'm presenting this project today here, and the project is co-coordinated by Oksana, who's also connected, and me. But there's a lot of different people and a lot of different projects behind all of this that make it happen, because there's so many different libraries here and services that we're using. So thank you very much to everyone who has contributed in one way or another. There's a large group of people behind all of the different projects. All right, and then with this, we're going to transition over to the notebook. And the notebook now is going to bring us throughout a physics analysis, all the way from reading our input data to getting some results through statistical inference. You're welcome to follow along on Binder. And I'm going to have a Slido open in parallel. And since we're going to be hitting on many different pieces here, please feel free to put questions on Slido anytime. I'll try to address them as they come up, because we're going to be moving through different pieces, and it might be easiest to sort of address the question right when we're talking about the respective piece. I'll also try to open the Zoom chat, and I see a first question. The mailing list is open to anyone. Yes, the sign up link there is open to anyone. You're very welcome to sign up to that list to follow the developments. All right, and then with this, click the link on Indico if you want to follow along the notebook yourself. And I'm running on Coffee, as you can see up here in the URL. So up here is just a bit of an introduction of what I just already told you about. And then the first image here in this notebook is, again, the kind of pipeline that we're looking at. And what's also here now are all the different logos of the different libraries we're using here. So just to give you the overall large-scale plan of how we're going through this. We're going to have some columnar data. That is our input. We're going to read that data, filter out the events that we care about, evaluate systematic uncertainties, construct observables we want to use, and then fill them into histograms. We take those histograms to build a statistical model, which we then serialize in a so-called workspace. And then once we have that model available that we then saved in this workspace, we perform statistical inference, get out results, and visualize them, and then we can go on from there. We're going to go through this pipeline in two different ways, but then you will see that we're going through them in two different ways that have different advantages associated to them. There are links here to other talks because we're going to be touching, like I said, on lots of other projects, so please check them out for more details on the various pieces that we're using today. Okay, that is enough preamble. We're going to start out by setting up all of our inputs, all the libraries we're using. And the very first thing you're going to see up here, the very first piece of content, is this thing we call AGC schema. So AGC stands for Analysis Grand Challenge. So this is the project that we have here. And what this schema is doing is that it will group all of the columnar data that we have together in order to make it really convenient for us to access. And since that might sound a bit abstract and this might be a bit hard to read, instead of going through that in detail, let me just show you what this schema does exactly. And we're going to do so by exploring a single file of data that is in our data set. It's typically a good idea to start out by exploring something quite small, because then with this, we have a fast iteration time. So if you start executing the cell here, you're going to download a 200 megabyte file, just as a warning if you're on a limited data connection. We have it already, so here in this case, this runs quite quickly. And then what we can do here is we can open this file just read it with uproot. And if I uncomment this line here to look what's inside that file, then we're going to get the list of all the branches inside that file. And you see, okay, there's quite a lot of branches in here, quite a lot of information. And now you can go on from here and you can use Awkward, for example, to start analyzing your data from here, no problem. However, we're going to be using Coffee in this demonstration here. And what Coffee gives us is this possibility to specify this schema that we just looked at in the cell above. So let's do that and let's see what we get out in this thing that is called events, which is what we get from this nano events factory reading that same root file that I just opened manually with uproot. And now suddenly we just get a few types of fields out of that correspond to different physics objects. And we have grouped essentially all of the columns that we care about into these objects. And now we can reason about the data that we have in terms of these objects. So it's much more convenient to now use those, because everything belonging to jets, for example, is grouped together under this jet name. And we also have behaviors associated to this so that we can add jets together. And then in the background, automatically the addition of these 4 vectors is done for us. So we don't need to think about it. It just works automatically in the background through what coffea provides here through this schema. You can also accomplish this with awkward directly if you want. So just to demonstrate here, we can now access, for example, the jets in the event, and then we can access .pt. And now what we get out of that is the PTs of all our events. You can see there's about 42,000 events in that file that we're reading. And then there's a variable dimension here, because in each event, we're going to have a different number of jets. And then this is the PT then per jet that we have. All right, so now let's just have a brief look at our data. Let's just see what's in there. So what this line does here is it counts the number of jets, which is what this here is, per event, and puts that into a histogram, which we're going to construct with hist. And then we get this nice visualization here. And we can look at it and see, okay, there's actually quite a lot of jets. So this peaks somewhere around 10 jets or so. And you'll see in a second how TT bar this topology looks like if you haven't seen it before. But I can tell you already right now, that's quite a lot of jets. So that might be a bit surprising. However, what we can do is we can filter out all of the jets that have really low transverse momentum, which we're typically not going to care about much. And we're going to do that here and plot the same thing again, this time calling here .plot and then plotting through matplotlib. You can see the same distribution here where we have now plotted again the number of jets. After this requirement of each jet should have 25 GeV in PT. And now we're peaking somewhere around 5 or 6 jets, which is more reasonable, what you would expect when processing this type of data. Okay, let's now do one more thing with this data and to show you a bit more of the columnar processing we can do, which we're then also going to stick into coffea. So what we have here is the production of top quark pairs. We have incoming proton beams, they collide, they produce a top quark pair, which are the 2 red bubbles here, if you want, and those decay into bottom quarks and W bosons. And then everything that's surrounded here by a black circle is what we can observe, or rather the remnants of that ultimately what we can observe in our detector. So some of the things here we cannot observe, like this neutrino down here. But in this type of topology we're looking at, we're going to expect 2 of these B quarks. We're going to expect 2 additional quarks here. All of those are going to create jets in our detector, and 1 charged lepton down here. So this is everything that we expect. And now what we would like to do is reconstruct the mass of one of these tops. And there's one way of doing that, which is by identifying that the transverse momentum of these top quarks is going to be balanced, assuming that there's nothing else happening in the event. And then we can just pick the pair of 3 different jets that maximizes the transverse momentum when you sum them together. So in this case here, that's typically going to be these 3 jets up here. One of them is going to be B-tagged, and then there's 2 additional ones. And if we sum all of them together, we're going to get something that resembles the top. Now, this is a statement that I made, but let me prove to you that this actually works. And this is down here in this cell, which is sort of like the algorithm that we're going to use. Again, just using awkward, we're going to look at our events and the electrons, muons, and jets, and select all of those that have transverse momenta above 25 GeV. Then we're going to look at events that have exactly 1 lepton, which is what the line down here does, at least 4 different jets, which we expect from the event. And one of them should be B-tagged, which is down here, because, sorry, at least 2 of them should be B-tagged because we have 2 B quarks in our event. We apply all the filters, and then down here is a bit of awkward magic to make things happen. So we're looking at the combination of 3 jets that maximize the transverse momentum. So let's just calculate all of the possible combinations via awkward down here, get the 4 momentum of the of this 3 jet system for all of the different combinations, make sure that there is at least one BTEC jet down there, which is down here. We're checking that the maximum BTEC from all the 3 jets is above threshold. And then we take the system that maximizes the PT, which is what this is, what's down here, and calculate the mass. So that's a lot. Feel free to take a look at it again afterwards to convince yourself that we're doing the right thing here. Ultimately, we fill everything into this variable, and let's plot it and see what comes out of it. This is the distribution compared to where you expect the top mass to be, somewhere around 175 GeV down here. It looks pretty good. So we have nowhere used this assumption that about the top mass being at this value, but still we're peaking around this value. So the algorithm seems to be working. Okay, so now we have a simple kind of setup, a simple algorithm that we might use to build some kind of observable and to construct a histogram that we might want to use in our analysis. Now let's start scaling things up. And the way that we're going to do this is by using coffea. There's a bit of configuration now up here where you can specify how many files you exactly want to run over, up to 3.5 terabytes, but I don't recommend doing this on Binder because you probably will run out of memory and it will probably take way too long and your Binder instance will not make it. So I would suggest leaving it at all the default values if you are running and following along on Binder. Here's the data pipeline that we're now looking at next. We have our input data, which is shown here in green, and then we're going to use coffea. And what the different bands here are representing is coffea processing a chunk of our data. The time runs here from left to right, and we're going to be able to parallelize the processing of all of these different chunks in this MapReduce pattern here that we're using. We're doing the same types of operations on all of our chunks of data, and we're writing out histograms, which we then in the end aggregate, we sum them all together and get out a single histogram ultimately. In fact, we're going to get out many different histograms, but we're going to sum all of them together. There's a bit of global configuration up here. We're just going to go through that. We don't need to change anything there. We're going to come back to this a bit later. So what we need next then is a processor that we can use to do this type of data processing. The processor is defined down here. Let's look at that first, and we are going to come back up to these variations up here. We're going to have a histogram. This is a multidimensional histogram, and this is where we aggregate all of our data. So what do we have in this histogram? We have one axis, which is going to capture the observable that we're trying to build here. We are going to have another axis, a categorical one, which is going to correspond to 2 different regions of phase space that you will see in a second. We have a selection where we request 4 jets and exactly 1 BTEC, and 4 jets and 2 or more BTECs. 2 different phase space region on this axis. We're going to have another categorical axis that corresponds to the type of physics process that we're filling in, and yet another one to the systematic variations. We need to consider systematic variations here because there's uncertainties related to many different things, and we want to capture them so that we can propagate them and ultimately correctly use them in our statistical inference so that we get a result that's not unrealistically optimistic just because we forgot to take into account some uncertainties that do exist. We can take advantage of metadata that you will see in a second coming back to read out information about the data that we're processing. And that can be very useful when you're using coffea here because you might want to specify additional information about all of the different files that you're processing. We're going to normalize all of our events to the luminosity from 2015 that CMS recorded, which is what we're using here. And then what's happening down here again is what we just looked at above, just doing it standalone and awkward. We just took that code and we put it into our processor. We do the same type of selection, selecting events that have 4 jets, at least 1 BTEC here, and a PT requirement on all the different objects. And then we're looping over the 2 different phase space regions that we're looking at here. In the region with 2 jets, we have the same type of algorithm that calculates this reconstructed top mass. And we have yet another region of phase space that we're also using here, where we have a different observable, the scalar sum of jet PT that we're filling in there instead. And then at the end of the processor, what's happening is this histogram object that we have that has all of these different dimensions here. We're just filling that, and we're filling that for all the different systematic variations, but we have all the histograms that we might want to need in here. So let me go back to these systematic uncertainties because they're coming up here. We defined a few functions up here for various types of systematic uncertainties. So let's look at this one, for example, which is the jet transverse momentum resolution here. What it takes is the transverse momentum of a jet. And then what we have here is essentially, we're calling a random number that smears our jet PT around a bit to kind of simulate that we might be overestimating how good our resolution is. So we're smearing things out a bit here. Now, in practice, if you're doing this in CMS, the function is going to be looking a bit more complicated. And ultimately, what you would do, for example, is you would call correction lib as Nick has presented. But what we care about here is just showing the workflow. So instead, the demonstration here just uses a simple function that captures the essence of what we're trying to do. We're going to call a function that gives us back a new variate jet transverse momentum. Now, if you do something like this that changes your transverse momentum of a jet, then that has implications. So we need to, for every systematic uncertainty, we need to do the exact same analysis pipeline here. We need to do the same type of calculation, but the calculation will be different depending on the properties of our objects. So if the jet PT changes, for example, since we have down here a requirement where we say we select jets that should have a PT above 25 GeV, now this needs to take into account that this is going to vary as a systematic uncertainty if you do apply this calculation up here. And that's why we fill it here in an additional additional property of this event, which is up here, where we say, okay, actually the PT is going to vary, and we take that into account and we propagate that through our processor. So there's different types of uncertainties that we have up here, some which only change the weights of the different events and some which change the properties of objects. And I think I will leave it at that level of detail right now. I'm happy to go more into this if there's questions. But this is something that you will have to deal with when you do this in practice. And this can make your logic of the implementation of your physics analysis code significantly more complex depending on how you approach this. So for now, let's accept that cell. So we have a processor available now. What do we need next? Okay, we have something that does our calculation, but we need to construct the actual input. And you will see here that we are calling out in the cell to a utilities file that contains a bit of code just to not fill up this notebook too much. And then effectively what we're getting here is a dictionary that looks like this excerpt down here. So this dictionary is going to have different keys, which are up here, which are different physics processes, production of top quark pairs, and then various different ways of doing this production corresponding to systematic uncertainties, ultimately production of single top and production of W plus jets as well. The different physics processes here are going to be associated to a list of files, and those files up here are publicly accessible. You can use them yourself, and there's metadata that we associate to it as well, such as the cross-section for a specific process, which we're then going to be able to access in the processor in order to make use of it. Okay, so we have a processor that does the data processing. We have constructed the input in this big dictionary here that we want to process. So it's time to actually execute everything. And that's here in this next cell. I'm going to hit start, and you can see there's a progress bar happening. There's two steps happening here. The first is the pre-processing stage in Coffee, where we just look at our files. Essentially, we check how many events are in there, and then Coffee splits it out into chunks of work. The second step that just finished is the processing stage, where we then actually call the processor code to do the execution. You see, this finished very quickly. And the reason this finished so quickly is because we're only processing a small number of files in here. This is only about 2 gigabytes. We'll scale it up in a second. But if you're running along on Binder, this might take a bit longer because you're going to stream these 2 gigabytes essentially to your Binder instance. So this might be slightly slower. So what we got back then from running Coffee is this object here that I called all histograms. So let's see what's in there. So if we just add it down here in another cell, you see this is a histogram with all the different axes here. And because we're going to have a high dimensional object here, maybe let's do some plots in order to have a better idea of what's in this histogram and to convince ourselves that we produce something sensible. All right, so the first plot that we have down here is now the plot of this phase space region where we select at least 4 jets, and one of them should be V-tagged. And let's see the types of processes that contribute here. So we have TT bar, top quark pair production. contributing here in this yellow color, as would be expected. And then there's a big contribution here in purple from production of W plus jets, which also makes sense because we only require a single B tag. So if you're working in this kind of topology of phase space, if you're looking at this plot, this looks like a sensible outcome. So everything here seems to have worked. Let's also look at this other region of phase space that we already processed, that we already took a look at when only processing our single file up top, which is this region where we have now a requirement of 2 B tags. And this is now where the top quark pair production really dominates. So almost everything in here is yellow. We see again a nice peak around the top quark mass. So still things seem to be working. The difference to the simple example above is that above we just processed a single file. Now we've processed all these different processes as well, not only the nominal distribution, which we're looking at here, but also different systematic variations. So let's take a look at that, because so far you haven't seen the systematic variations. So let me convince you that we actually did process them. And we're looking at them down here. What's cool here is that we using features like this specifically is what HIS gives us through this universal histogram indexing. We can rebin the histograms just on the fly, merging bins together. We can just do it like this. And we're looking here now, we're slicing at this region of phase space with 1 B tag requirement at the process of TT bar and at different systematic variations. We're plotting all of them. And you can see here now that there's different distributions. So indeed, our predicted template for the different TT bar distributions here under the systematic variations changes a bit. So this systematic variation does have an effect on our results. So we better take it into account when we move on to the statistical inference. We've not only done B tagging variations, we've done other ones. We have some jet energy variations, for example, that we're looking at down here. You can see those look a bit more similar to each other. There's a small effect here only, but you can also see there's different histograms that were all filled, and they slightly differ from each other. Okay, so we have everything in this high dimensional histogram. Let's make sure we're not losing it. So let's save it to disk. There's a utilities function. Feel free to take a look at it. It's in this folder called utils, which if we move into it, is down here. It's this function up here. If you're interested in taking a look, it's not really doing anything interesting. It's just going through that file and saving everything to a histogram in that root file. So we have that all now saved. We have all of our histograms saved, which means it's time to move on, build actually a statistical model from that, and perform some inference. What we're using here then to accomplish this task is this library called cabinetry. And the very first thing you see down here is that we're loading a configuration file. So we probably better have a look at what's inside that configuration file. And let's do so. This configuration file now specifies in sort of like from a high level viewpoint and from kind of a physics viewpoint, what the statistical model that you're building should contain. So there's a few settings up here. We're not going to go through everything in detail. There's not enough time for this, but you're welcome to check out the previous talk on cabinetry at the last PyHEP that is linked at the top of the notebook. So we have a few physics concepts here. We have different regions of phase space because we filled 2 different regions of phase space. So we specify them here. And we also specify a path because ultimately all of our histograms are going to be looked up in this path that is up here that has a few placeholders, and everything that's a placeholder like this region path thing here is going to be filled in by the options that are specified down here. Then there's different samples available. We process TT bar, W plus jets, and so on. There's also this thing here called pseudodata. We're not actually fitting real data that CMS took. We're building our own pseudodata version of that. Reason for this is mostly to avoid any kinds of issues with the data being in bad agreement, because we're cutting some corners here. So we're just building a pseudo data set ourselves that is in reasonable agreement with data, but there's nothing with the Monte Carlo prediction, but there's nothing fundamental about this that prevents you from using actual data here. So we enlist all of the different samples. And then lastly, we enlist all of the systematic variations. Again, and we have some configuration options for each of the systematic variations that tells you how it's built. And it's referring back then to all of the different histograms that we have just filled into our histogram root file. And lastly, there's normalization factors. So we have one normalization factor here, which we call TT bar underlying norm, that acts on TT bar. And that is the thing we want to measure. We're going to measure the normalization of this TT bar process, which then is proportional to this TT bar cross section. Okay, so that is how the configuration here looks like that we just loaded. Let's move back into the to the talk. And what we're going to tell Cabinetry is then, okay, look at this configuration, collect all of the template histograms that are specified in there, and build a workspace. And then for completeness, we're also going to save that workspace to a file. You don't need to save it, but just let's keep it around. Let's save it to a file, which we did here. We can take a look at it. And what we have down here now is a PyHEP workspace. The visualization of JSON files here on in this case is a bit difficult to see maybe, but if you download that JSON file and you view it in another editor, you can see now the structure of this workspace, which contains the statistical model that we're going to be working with in this JSON format specified by and used by PyHEP. We can use now PyHEP to go ahead and do inference with that, and we can use also command line utilities here to take a look at that workspace. PyHEP provides this, and here's a summary of what's in there. 2 different channels, the 2 different phase-space regions, 5 samples, 40 different parameters. We have 11 bins per channel, and these are the samples down here. So PyHEP understands what this workspace is, because otherwise it would have complained here that it doesn't know how to pass that file. So everything seems good so far. Okay, so then let's actually take that workspace and let's perform a fit of the statistical model that we have here to data. That's what we're doing here. What we're doing is we're using Cabinetry to perform a maximum likelihood fit. Cabinetry calls PyHEP to do that, and PyHEP actually calls IMinui internally from how we have configured it to perform this likelihood maximization, or rather negative log likelihood minimization. So we're getting out of that the status report here. Everything is good, which is good to see. The uncertainties and best fit values for all the different parameters. And we can also visualize the results of this fit. Down here are the results for all the different nuisance parameters with how pooled and constrained they are. If you are now a physicist, you might get very worried about how constrained these 2 parameters are down here. That is essentially because they have very large effects. They shift the prediction by quite a lot. And we have an incomplete model here. In practice, you're going to add additional nuisance parameters, which will relax all of this a bit. So don't overinterpret this in terms of physics. Again, this is just a demonstration of the workflow here. You can get all of the usual things you might want to look at back from this. So we can look at the correlation matrix, for example. Here you'll see the correlations between all of the different parameters. We can look at, okay, what was actually the best fit result for the parameter we wanted to measure, this normalization for TT bar. You can see the best fit value is very close to 1. So it's an agreement with our prediction, or if you want, it's an agreement with the standard model with an uncertainty of about 6% here. And if you've done this fits, you probably also want to see, okay, how are the distributions looking that we actually fitted? You can see the distributions before the fit is performed alongside uncertainties here with all the statistical and systematic uncertainties. You can see the uncertainty band is quite large before the fit is performed. We have them in both the regions of phase space that we fit here. And we can also calculate the post-fit version of this plot where we now project the fit results onto this. You can see we have significantly constrained in this profile likelihood fit all of these uncertainties, the uncertainty band, to the statistical power that we have from data. And everything is in very good agreement here. The model fits our data very well. Okay, so I'm going to show you one more thing down here, which is some upcoming features in Cabinetry, because we're actually using a version that isn't even released yet here, just to give you a bit of another look at this statistical model that we just built. And what this function here does is it visualizes the structure of this model. So the structure of this model here in this kind of visualization looks at the different phase space regions that we're fitting, 2 of them. This region with 1 BTAG, this region with 2 BTAGs. There's different samples available, the different physics processes that we have. And then there's different parameters available. Those are the parameters that were used in our fit. And then what the different colors here tell you is what types of modifiers are acting when you change a different parameter, what happens. So if like something here is green, for example, that means this parameter controls 2 different modifiers on a specific sample in a given phase space region. So this, if you are familiar with PyHEP, tells you a bit of how the model looks like in terms of its structure. You can visualize this in different ways. This way, because inherently the information is sort of three-dimensional, there's three axes here, and we can't easily visualize three dimensions, so we split the third dimension essentially into two different plots. And there's two different ways to plot this. You can, instead of splitting it by phase space region, you can split it by sample and do the same type of plot. And depending on what you might be interested in, one or the other of the visualizations might be more useful. You'll also get you can also get tables out of this with uncertainties. You can actually save them as LaTeX or as any other format, as Markdown, as HTML, as anything you really want, via this tabulate library that is being used here. Here's just an example of the yield uncertainties for all the different samples and the total model prediction after the fit has been performed. Okay, so now we essentially have the pieces that we can put in our paper. We can put this kind of table in our paper. We would probably want to put these type of plots in our paper. We have the results for the parameters that we fitted. So we're good in some sense. Now, one thing is we only process a small amount of data. So let's try processing a slightly larger amount of data. Before I move to that, let me check Slido and Slack to make sure I'm not missing anything important. Okay, looks like not so far, but feel free to ask something if things come up. So let me move ahead and show you what happens if we process a bit more data than before. So on Binder, you have this value up here set to 50, set to 1. I'm going to set it to 50 now. And we're also going to use task. On Binder, that's false by default. We're running somewhere here where we can actually scale out a bit and use more resources at the same time. So I'm changing the settings up here, and I'm going to run through these steps again. And I'm again doing the step here, executing the data delivery pipeline. Now I'm moving over to Dask here, and what you see now here is the stream of tasks that Dask is processing, and it's already moving quite rapidly because everything in yellow, that was the pre-processing where we just look at all of the different files, and we take a look, we see how many events are in those files, so that we can then split it up into chunks of work that need to be executed. And those are then being executed. That's everything that's here in blue. You see we're already halfway done with that as well. So here, now what is happening is Dask is going to run jobs that process all of the different chunks of data. And this is happening here in parallel on multiple different threads. And then once this is done, every piece of work here is going to produce this 5-dimensional histogram. In the end, everything gets accumulated back, merged back into this one master output, and we just get these the same type of histograms back that we had before. So this object is going to look the same, with the only difference that we process more events now. So our statistical uncertainties are essentially going to be smaller. But we can run, again, the same steps that we have run before, and we're going to get the same types of plots out of it. We did the same thing, we just have more data available. So I'm going to go back through the same stages that we just had, which are all going to give us the same outcome. Now, in practice, you want to scale here to many hundred cores at the same time, ideally, so that you can really have an interactive type of workflow where your analysis runs so quickly that you ideally can spend your time then looking at the results, studying the results, making conclusions of what to do next, and you're not being blocked by things that take a while where you're waiting on them. Now, if you are running on Binder, there's one thing, I saw in the chat, it was actually quite fast, apparently, but there's one thing that might be making things really slow if you're running with a larger number of files. And that is the problem that we're currently streaming all of the data that is being processed to Binder, or in this case here, to this notebook that I'm running at this Coffee Casa instance. And in order to address this issue, we're going to look now at a different data processing pipeline. And this is where Service X comes into play. So if you were following yesterday, you will have seen Kyungyeon's talk where he already presented Service X. So let's take a look at how we're making use of it in this setup. The first pattern up here is what I've shown you already. We have our data. Our data is accessed by all of these different coffee processors running in parallel, processing chunks of that data. We aggregate everything back and we output this big histogram. But the data being streamed here is all of the data, potentially all of the columns we might want to access. And it also doesn't really include any kind of pre-selection. So if we know, for example, we're going to only care about events that have lots of jets in them, we could, in principle, reduce the amount of data that needs to be transferred at this step if we already selected only those kinds of events that fulfill the requirements that we might want to make. In practice, at this stage of physics analyses, your jobs are often going to be limited by the input and outputs, so just by the transfer of data. And if this is a limiting factor, then you really want to reduce the amount of data that needs to be transferred. And one way in which you can do this is you can have another step running at first, which reduces your data already, so that you're then only sending further additional data that's really needed for subsequent processing. And if we use service X here, what will happen is that we're going to have another step at first, where we set up a query that specifies, okay, this is the data we really need. This data is then going to be processed by service X in parallel at sites running ideally very close to where the data is stored. So the transfer of data can happen very quickly. And then what you get back, sent back from service X, is only that data that you're going to really need for subsequent processing of your data. And that can actually speed things up very substantially. So if you're running on a slow internet connection and you're running this whole thing locally, for example, then you will see that that first stage, this type of processing, can take forever. So I can tell you for reference, on a slow internet connection that I had a few days ago, this takes about 10 minutes. And this pattern that we're showing you now takes a few seconds in comparison, because the amount of data is going to be drastically reduced. So let's take a look at how this works. We're going to first set up our query. This uses funcadl. There was not a contribution about this at this workshop, but there was one at PyHEP2021 if you want to take a look. The query that we have here is actually quite simple. We're not making any kind of event selection. We're only saying these are the different columns that we want. So if you look back at our input files, those are all branches in that file. And those are all the branches that we want to use. So the query here says, look at that file and select all of the columns that match those names, and please return them to us. So that is the request that we have. We then need to send that request off so that it can actually get processed. There's one small hack here. Don't worry about it. Read the details here if you're curious. This is only for demonstration purposes to reduce the amount of code here. We're going to need a different base class for the processor that we defined above, but otherwise the processor is the exact same. So our workflow will look the same other than this like tiny change here. So it's essentially the same type of setup we had above. And now again, we're going to execute everything, which means we're going to start this by sending to service X the request, please process this data. We're getting the request back. And as the data comes back asynchronously, Coffee will start picking up the data that is coming back and start processing it. And once everything is done, it will return us again this object with all the different histograms inside. Now, what you'll notice up here is that we're generating a unique name. So if you're following along, you will also generate a unique name now. And the reason for this, you'll see in a second, because as I launch this, we get a unique name now, Sweet Sidewinder. And you can see multiple progress bars appearing for all the different processes that we care about. And there's two of these process bars per process. The first one is going to be the processing of that data. So like service X actually doing the data processing. And the second one is then us downloading that data again to the place on which we're running. I'm switching over to the dashboard now here, where we can see the progress of service X, and I'm going to update it. You'll see here some earlier runs that I did. And they all have names associated to them. And the reason that I give everyone a unique name is that if you're running and you're also following along now, you will also start appearing here. And I want to identify which one I am, and like you can see your unique name. So that's why everyone here has a unique name. So you see here the different things here that are called Sweet Sidewinder. This is everything that I just launched, because that's my name that was assigned for me. You can see the progress of these different tasks, and you can see we're already quite far advanced with most of them. The first ones here have already finished. Many of the files are completed. You can see they're processed by multiple workers in parallel. So here we can really also scale. If we have a large amount of data that needs to be processed, then Service X is executing this for us at scale. This is now running at the University of Chicago, this instance of Service X that is doing the data processing. And if we switch back to our notebook, you can see that the processing is happening, but also the downloading is happening, and we're fully done now here in about 100 seconds. We talked to Service X sent us back the data, and then coffea processed this data. And we're using still DAS because we have it enabled, and you can see now looking at the stream up here, the different jobs that process these data. There's lots of gaps here because ultimately we're waiting on the data to arrive back. And then once the data is there, the processing is actually very fast because there's not a lot left to do. And that's why there's some gaps in here. But Dask has now also processed all of the data, and we're fully done. So we got back this object called all histograms, and then we gave it a new suffix here, Service X. And the reason I gave it the suffix is to now show you that we actually get the same thing. And that's in this next cell down here, which I can run. And you'll see that nothing happens in this cell. That might be a bit underwhelming. So let me just add another type of printout here, which is going to say that everything agrees. And what this does is it loops over all the different axes in our histogram, over all the different dimensions, and it checks whether the two histograms we produced, those we produced with Service X and those we produced just with plain coffee, are in agreement. And indeed, you can see they are all in agreement. We get the same data out of it, which you would expect, right? We're doing the same type of data processing. We're just using a different pipeline where we have this additional Service X instance running in front, which can help us run things more efficiently. If you look at it in detail, you will see that we're skipping one specific variation here. That's due to technical reasons. One of the systematic variations that I showed you up there was computed, including random numbers. We're currently not fixing the seed to get some deterministic outcome here. So these histograms are by design varying every time that you run them. So it doesn't make sense to continue this variation, but everything else here is in good agreement. So everything here looks good. All right, and then with this, I'm at the end of the demonstration. I want to say a few last things here about what's next for this project. And the first thing here, as I was already alluding to on the slides, is to add more features here. Machine learning is something that has been requested, and that we also would like to add to this demonstration because it's quite relevant to people running physics analysis. There's typically machine learning components in there nowadays, so we would like to get this added to the setup. And what we're moving to next now, actually, and what we're working towards for another conference, ICAT, happening next month, is benchmarking the performance of all the different pieces in this workflow, and then subsequently also addressing bottlenecks that we're identifying. So we've already been working on this a bit, and we found things and we addressed things that can help improve the performance of this pipeline, and we will keep working on that. We're also very interested in seeing different implementations of this analysis task. And I think there's a lot to learn if you can have one type of benchmark analysis that you approach from different angles with different implementations, and you see how they compare, what the usability is like, and everyone might have different preferences of like how they approach something. And I think it's interesting to see this, to exchange ideas, and to potentially find better solutions that then also might translate to other types of implementations. There's a root R data frame-based implementation you can find linked here. There's also a partial implementation we have that's written in Julia. You're very welcome to check them out if you're interested in that. And if you have additional implementations you're curious about that you would like to give a try, they're very welcome. In this repository here, there's also a plain text description of what this analysis task is, what it all includes, which might be useful. So you can work against that when you write something instead of having to work against the code here. That's sort of the reference implementation for this analysis task. And then lastly, a goal really here is also collaborating. And what that means is if you really have anything connected to this where you're like, oh, I would be interested in looking at this kind of aspect or adding this type of feature or investigating something, then please do get in touch, because we hope that this can be a project that can be useful to the community. And I think it can be in many ways. If you have any type of software libraries that you're working with, that you're developing, that you might want to test in practice, and that you might want to test on public data so that you can actually also easily show them off without being restricted by the requirements that the different experiments have at the LHC, then this might be a good use case. If you're working on analysis facilities and you might want to benchmark physics analyses, you could use this as well. And maybe you're just curious about how you might want to do analysis at the high luminosity LHC. So please do get in touch. Again, there's a link to the mailing list down here. And there's also a link to the main repository that we're using. This demonstration today was based on earlier work that we did and another workshop we had run. And there's more information, more links in this repository. So please feel free to check them out if you're interested. And with that, that's everything I've had. And I see now there's a question. So let me take a look at that. And then if there's anything else, I'm happy to address them. All right, the question is, how large of a cluster do you want to run the final demonstration on? This was 10 workers with 1 terabyte, so 4,000 workers with 400 terabytes. All right, so I think there's two pieces to this. So there's the one question, which is, what kind of cluster would I like? And the answer to this is essentially like as large of a cluster as I can get. And the other piece is sort of, what do you envision that people will actually realistically have in the future, right? So I guess the answer to the first one is we're going to work on all the facilities that we can run on. So we're working together with the operations programs US Atlas and US CMS, and there's various facilities in the US that we're all trying to get this set up. On multiple of them, we're already running this. So realistically, there you're going to get hundreds and ideally thousands of cores that you can run on in parallel, because really one of the goals here is to see, is it realistic to have this kind of interactive analysis workflow where you start this notebook and you're done within a few minutes with all of the different pieces that are done. And one thing actually I didn't show, let me run it now in parallel while I'm answering questions, is that one thing that's crucial for interactivity and for fast turnaround is caching. If I run this thing up here again, which took 100 seconds before, let's see how long it takes this time, because it's going to be much faster. And the reason it's going to be much faster this time is because all of the data is cached that we used previously. So this time, when we run this a second time, and you can try this on Binder as well, you're not actually going to run service X again, because all of the data is already there, so you only need to run the coffee step. So this type of thing, this sort of caching, you see now it's 25 seconds, it was 100 before, is crucial if you want to really be interactive. Okay, and another question from Matthew. You already did a bit, but can you talk more about the coffee casa deployments at different analysis facilities and who can access them? Okay, right. I don't have slides for this, but I think we probably have slides in the introduction from the last workshop. So if you go here, the workshops are linked, and there might be you might be able to access it from there. There's information. So we do have one facility, the one actually that I'm running on at the University of Nebraska-Lincoln, that is open, where you don't need to be on a specific experiment in order to access it. And you could get there with your certain credentials. There's other facilities in the US specifically, where I'm most familiar with them, that are then typically restricted to either CMS or Atlas. And you can, again, depending on the facility, log in via different methods, for example, with your certain credentials. So for example, at Chicago, there is an Atlas instance, a Coffee Casa instance that's available to you. Then at Nebraska, there is another CMS instance, also Coffee Casa instance that's available to you. And then there's various other instances throughout the US at Fermilab, at BNL, at MIT, various facilities where you do need then specific credentials in order to get access there. If you're curious, though, I can look up the link. I can send the links in Slack so that the people who would like to check out the facilities can find where to go in order to get access. Okay.
Okay. I think we're at time, but thank you, Alex. That was a hugely impressive demonstration. So that was excellent.
Thank you.